Harold and Maude did not do so well in their coaster manufacturing business, but they've decided that they like working together, so they've started a new business. Now they're manufacturing floor tiles in the shape of perfect squares. Okay. So, of course, the area of a floor tile will just be the length squared. Okay. Their goal, they're making fairly big ones. Their goal is to have them be 2 feet on each side. And of course, that means that the goal for the area is 4 square feet. And so we've got area is a function of x here. Looks fairly similar because area of a square or area of a disk, both are just multiples of some number squared. Okay. They're confident that they can measure x with a possible error of 0.01 feet. Your job is to estimate the error and the percent error in the area. Now, if you feel comfortable doing that, go ahead and pause the video now and do that. This is relatively new and the notation is new, so I'm going to just get you started by sort of enumerating the tasks that you need to do and reminding you of the notation that we have. All right, so basically delta x, which we will choose to set equal to dx, is the error that we can make in measuring x, which is the side length. Now, realistically, if we're saying that they can measure x with a possible error of 0.01 feet, they're saying that the absolute value of dx is less than or equal to 0.01. But I've said I'm okay if you do what the book does and just set it equal to 0.01. What you're doing in that case is you're saying that's the absolute value. So just focusing on the amount, regardless of whether it's too big or too little by that amount, absolute value of the worst case scenario. And that's the scenario we want to make sure we're prepared for. Okay. So delta A is the error in the area. Okay. I'm asking you just to estimate that so we can estimate that with dA, with that differential. So you're basically going to be finding the differential for this function. Okay. And of course, you're going to be finding that at the moment in time where x is 2, the targeted value that we wanted for x, and dx is 0.01. Okay, excellent. So that's the amount of error. And then what percent error does for us is it really just helps us to put things in perspective. We get some number and we say, oh, is that a big deal or not? You know, if I were to measure the length of this whiteboard here and be off by a foot, I'm pretty bad at measuring things because 1 foot compared to the length of this thing, that's a huge percent of error. But if I were to measure the circumference of the earth and be off by a foot, I'd be doing a pretty good job of measuring things. Okay, so the same amount of error can be a big deal or negligible depending on what it was that we were shooting for. Okay, so delta A over A gives me the percent error in the area. This would give it to me as a fraction. I need to obviously convert that to a percent. Okay, so delta A over A times 100% is equal to the percent error in area. But we're going to just approximate that with dA over the targeted area, which was 4, and then convert that to a percent. Okay, so those are your tasks. You're basically calculating dA for this value of x and dx, and then you're calculating the percent area by putting that over 4 and converting that to a percent. All right, if you haven't already paused the video, pause now and do that. All right, I've got this worked out here. We determined that to estimate the amount of error in the area, we were going to just calculate the differential dA. So I said rise as slope times run. dA is going to be the derivative of that area function dx. Since area was just x squared, the derivative is 2x. We needed to evaluate that when x was our target for x, which was 2, and when dx was this absolute value of our worst case scenario, 0.01. So plugging in 2 for x and 0.01 for dx, we get 0.04 feet. And oh, I apologize, that should be 0.04 feet squared. Oh my goodness. That's because that's the error in area, and area would be measured in square feet. Okay, and then to convert that to a percent, we needed to take that amount of error, divide by the area we were shooting for, which was 4, and convert to a percent. So, taking that, dividing by 4, and multiplying by 100%, we get 1%. Okay. Now, I've got up here on the board this picture here that shows us a little bit of how this is working, but it's a little bit strange because here we're representing area as a height. The area of this thing is the y value, essentially, on that graph. Here's another way I can visualize what's going on. We're trying to manufacture these things of side length x. Now, I know my target for x is 2. In a moment, I'll plug in 2 for x. But right now, I'm just going to say x is my target length. We're going to make a mistake. So there's going to be a dx involved. Now, I'm going to draw it as if we just measured things too long, so that dx, our error in x, is positive, just to keep the picture a little bit simpler. Okay. So then we'd actually be getting the area of this bigger square instead of this smaller square. So what I'm shading in red right now is actually delta A. That's the error that we would get in the area because we measured the side length wrong. Now if I look, that can actually be broken up into 3 parts. There's this part right here that would have as its area x times dx, because it's got a length of x and a height of dx. This rectangle here also has an area of x times dx. This has a base of dx and a height of x. This little piece right here would be dx quantity squared, because its base and its height are both dx. If I look at this piece right here together with this piece, which do seem to make up the majority of the error, that's 2 copies of x dx. That's exactly what dA is. And you'll notice, if I were to replace x with 2 and dx with 0.01, that would be 2 copies of 0.02, which would give me the 0.04. Okay. So that illustrates the error that we're getting in area in a way that I think is a little bit truer to what area looks like. So kind of nice to have with this example.